Okay, so we are ready to um Megan, I see your camera is on. If you can just please turn it off, so just you're not recorded. Thank you. All right, so we are starting unit 5 today. Okay, the last slide in unit 4, it was just a summary, and it does say, the title itself says here, the various ways to calculate these thermodynamic functions. So delta H, delta S, and delta G. Okay, so this is what you're expected to know. We've gone over each method during the lectures. This one, the Van 't Hoff equation, like I mentioned last time, I see many students confusing it with the equation that we saw in Unit 1. The other day, I was stupid enough to be looking for it in Unit 2. I don't know why. It's here on page 41. We've seen this equation. In here, the K1 and K2 are rate constants, okay? They are not equilibrium constants. Okay, that's the difference. And the other parameter we have in here is activation energy. All right. And here in unit 4, the Van 't Hoff equation has these, which are equilibrium constants. Okay, so you need to know the difference between the two. And it has heat enthalpy of the reaction in the expression. All right. Know the difference. That's what I'm saying. So if you have a question where you're given enough information, where you can find equilibrium constant 1, and then if you're given the second equilibrium constant, whatever, or whichever you need to calculate, if you've got information about equilibrium constants and the different temperatures, you can use this equation to calculate delta H of the reaction. Okay. And the different methods to calculate delta G are here. All right, I'm not going to repeat these or read them again for you. We've seen each one of them in the lectures. Okay, so I will leave it here. And now we will begin Unit 5. So Unit 5 is about electrochemistry. As it says here, we will be studying the transformation of chemical energy into electrical energy, and of course the reverse, how we can. So let me say this. Spontaneous reactions, when they happen, they generate electrical energy. So all these energy that is stored in chemical bonds, they are transformed, they or spontaneously transform into electrical energy, which we can harvest from these reactions. But we do have other reactions that are non-spontaneous. Okay, so you mix these components together, nothing is going to happen. But if we want them to react, we can force this reaction by giving electrical energy. So therefore, we are converting electrical energy into chemical energy by forcing the reaction to take place. We'll be talking about all of that in this unit. So what we are doing here, this whole thing, it is based on what we call redox reactions. Redox is simply short for reduction and oxidation. Okay, so when chemical reactions take place, and if there is an oxidation in that reaction, it means there has to be a reduction also that has happened. Okay, we cannot say, for example, here's a chemical reaction and it is a reduction reaction. That is incorrect. If there is a reduction that has happened, it means oxidation has happened as well. They go hand in hand. All right. So both oxidation and reduction, they take place in a given reaction. That's why we call these reactions redox reactions. Now, a lot of time we can describe these redox reactions as a transfer of oxygen. So a gain or a loss of oxygen. Let's see, for example, here. If we heat iron oxide in the presence of carbon, what we see is iron oxide will be reduced to iron. So we can produce iron in this way. Okay, so we see here Fe2O3 has loss of oxygen. Okay, so we see here a loss of oxygen. Therefore, this process is reduction. Okay, this compound, we clearly see that it has been reduced into iron. On the other hand, carbon has gained oxygen and it has been converted to carbon monoxide. So this is a gain of oxygen, and I'm talking in terms of oxygen transfer here. So Therefore, this is oxidation. So very simple. All right. Now let's take a look at the second reaction here. Now we have sodium reacting with oxygen to form sodium oxide. So if we look at sodium, it is clear, yeah, how can we define this process? We can say, yes, sodium has gained oxygen, so it has been oxidized. But now if we want to use the same description as in terms of transfer of oxygen, what are we going to say about oxygen? Like I said, if there is oxidation that has happened in this reaction, it means reduction is also taking place. Okay, there cannot be one without the other. So what do we say about oxygen? Can we say that oxygen has lost oxygen? Does it lose itself? It's not a very good description, right? So for reactions like these, either where it's just weird to describe oxidation and reduction in terms of oxygen transfer, or other reactions where there's no oxygen involved at all, okay? That doesn't mean they are not redox reactions. So how can we define them as redox reactions? We will do that. We'll describe them as redox reactions through the transfer of electrons. Okay. So we will describe the redox reaction through the transfer of electrons. And this is what you will see a lot. Okay. This is basically what this unit will rely on. Okay, and to do that, what we do is we take this overall reaction and we break it down into what we call half equations or half reactions. Okay, so the first one we see here, sodium is being converted into in this compound, we know it is an ionic compound. So it is being converted into sodium plus ions, right? And I'm just going to balance it the way it is here. So 4 sodium atoms are being converted into 4 sodium plus. And how can that happen? You know that now. Metals, they lose electrons to be converted into cations. So I will write this. So sodium, each sodium is losing 1 electron. 4 sodium atoms, they are losing overall 4 electrons to make sodium plus. Now, this is what we call the oxidation half reaction or half equation. Okay, I will talk about what we mean by gain or loss of electrons in a moment. Okay, so this is oxidation. And then where are these electrons going? They cannot just sit there or float around, right? They are being captured by the oxygen molecule. And these electrons, they are actually then converting the oxygen into oxide anion. Okay, this is the reduction half equation. Yes, Bradley?
So is it then this movement of electrons that causes the electricity to be generated?
That's right. And we will be talking about that. Okay, so that's exactly what happens. This movement of electrons between these two half reactions is what generates electricity.
Okay, cool. Thank you so much.
Okay, yeah, we'll definitely be looking at those. So this is what is happening, right? So one reaction, one half reaction is generating electrons, the other one is taking the electrons. So that's why we can describe, that's how we describe this reaction as being a redox reaction. And we'll see definitions on the next page. Here, sodium is the one losing electrons. The loss of electrons is oxidation. Okay, and oxygen is taking, is accepting, is gaining the electrons. So that whatever takes in electrons is the one that is being reduced. So that process is the reduction process. Okay, so that's how we define this reaction in terms of transfer of electrons as a redox reaction. Okay, now we'll move on to the next page here. So we are ready for definitions, like I said. Oxidation, yes, Cameron?
So for that electron transfer definition of oxidation and reduction, is that only something we should be using in the case of ionic reactions or ionic compounds?
Not necessarily. Okay, there can be transfer of electrons between two compounds. Anytime anything is accepting electrons, it is being reduced. Anything that is losing electrons, it is being oxidized. Now, of course, the transfer of electrons, gaining or losing electrons, will change the oxidation state. So yes, there's no question about that. We'll be making ions. Agree?
Yep.
Okay, so here oxidation is the loss of electrons. We just saw that. Sodium lost electrons, so sodium was oxidized. So the species, anything that loses electrons, it is itself oxidized, and we call it the reducing agent. Okay, so sodium gave the electrons to oxygen. It is itself being oxidized, but in the process, it is producing the electrons that will reduce the other one. So that's why we call it the reducing agent. Okay, and reduction is the gain of electrons. Oxygen was gaining electrons, so it was being reduced. So anything that gains electrons is reduced, but it is itself called the oxidizing agent because it is accepting the electrons from the other one and helping oxidize it. Okay, so just know the definitions. A lot of students know this already, and many students find it just helpful to remember oil rig. Anybody? Yes, when I'm in the classroom, I can see the faces, so I see the reaction to oil rig. I know many of you learned that in high school. So O is for oxidation. So oxidation is loss of electrons. Reduction is gain of electrons. If you just remember that, then your definitions will be right. Okay. Now here, this is just a half reaction, and as you can see here, it is a gain of electrons. So this is the oxidizing agent, okay, or the oxidant as we call it. It is gaining a certain number of electrons and making the reducing agent. So this is known as the reduction half equation. Okay, anytime you see electrons are being added on the reactant side, that's the reduction reaction or half reaction. Okay. And of course, it is getting the electrons from the oxidation step. So that's how we see the exchange of electrons between the two. So this is oxidizing agent. And of course, this is for reducing. Now, the transfer of electrons, of course, like we just said, it will change the oxidation state, okay, of these oxidizing and reducing agents. And we can also look at oxidation or reduction by considering the change in oxidation state. So anytime we see, and we know definition of oxidation state, right? Oxidation state is the charge that is carried by an atom in a molecule. All right. Okay, I'll just write it down. Charge carried by or on an atom. Okay, so an increase, anytime we see an increase, and I'm just going to abbreviate oxidation state. You will see me do that a lot on the coming slides. So an increase in oxidation state means oxidation has happened. Okay, going back to this slide, we see sodium was in an oxidation state of 0. It had no charge. Now it has a charge of +1. So that's an increase in its oxidation state. So we can say it has been oxidized. Okay. So an increase in oxidation state is oxidation. A decrease is, of course, reduction. And same thing going back to that reaction on page 1, oxygen was 0 initially, and then it ended up with a -2 charge in the oxide anion. So that's reduction. Okay, decrease in oxidation state is reduction. Okay, on the next slide, and as you can tell, I have already annotated it for you because this is something you have learned in Chem 101. So I'm going to go over it briefly, but just stating the key points that you need to know. Okay, this is important because you will need to know how to assign oxidation state of elements in a given molecule, because next what we are going to do is learn how to balance these complex redox equations. So this part is really important. If you can't find oxidation state, you will not be able to balance these equations properly. Okay, so yes, first thing that you need to know, if you're looking at a diatomic homonuclear molecule, okay, any molecule as long as two identical atoms are bonded together, it means the oxidation of each atom in that molecule, okay, is 0. So that can be the hydrogen molecule. Each hydrogen has oxidation state of 0. Same thing for oxygen, nitrogen, chlorine, anything, as long as we are looking at a diatomic homonuclear molecule. And now for hydrogen, that's the next thing you need to remember. In any molecule, if hydrogen is bonded to a non-metal, its oxidation state is +1, always. Okay, so that can be a molecule of HCl. So we see in HCl, it means that hydrogen is +1. Therefore, the oxidation state of chlorine in this molecule is -1. Okay, the sum of oxidation states in neutral molecules always add up to 0. But if hydrogen is bonded to a metal, then things are different. Then it has a -1 oxidation state. And that we see what has happened here. My example was NaH. And the oxidation state of hydrogen in here, it all got messed up. I don't know why. So oxidation state of hydrogen is -1 here. And it makes sense. Sodium is a group 1 element. It is +1. Hydrogen is -1. Overall, we have 0 charge. In the other hydride, a hydride of calcium, it means we've got calcium 2+ and 2H-. Okay, each hydrogen again, oxidation state of -1. Then you will come across compounds that have oxygen in them. Now, oxygen, it will have an oxidation state of -2 in all of its compounds, except for 2 types, which are the peroxides and the superoxides. Okay, you remember we did, if you took 101 with me, we did talk about that in Chem 101. When we have peroxides, oxygen will have an oxidation state of -1. In peroxides, oxygen has an oxidation state of -0.5. Okay, now we have a few examples here. Carbon dioxide, carbon monoxide, simple oxides of any element, oxides of oxygen, any oxides of different elements. Mostly we will see oxygen is in the -2 oxidation state. Okay, so that's general. So therefore use that to find the oxidation state of the other element. So here carbon has to be +4. Now, if we look at H2O2, here use what you know about hydrogen. Hydrogen, it can only be +1 or -1. If it is bonded to a non-metal, it is always +1. Here it is bonded to oxygen, so use that to find the oxidation state of oxygen. When we do that, we see then oxygen is in the -1 oxidation state, so therefore this is a peroxide, okay? Not a regular normal oxide. I see there are questions. Cameron, is that from before?
That's
Yeah.
from before.
Yeah. Bradley?
Sorry, I'm just not familiar with the term superoxide. I've heard of peroxides, but not superoxides.
Yeah, so they are just compounds in which, like I said, in which oxygen has a -0.5 oxidation state. And these oxides can be formed when we react like group 1 elements and group 2 elements with oxygen in a limited supply.
Okay, so would that be like sodium oxide kind of thing?
Yeah, like we have an example here, like this potassium, this is a
Okay.
superoxide. So this is potassium superoxide. And we see the trend also mostly as we go down the group, we will see these elements, they are able to form these superoxides, okay, in limited amount of oxygen.
So is the proper name for that then potassium superoxide, or would it just be
Yeah, yeah,
potassium oxide?
yeah, potassium superoxide.
Okay, cool.
All right. So here we are using again the oxidation state of the element that we know for sure. So here potassium is a group 1 element. So there's no other charge that is possible for it. It's only +1. So then use that to find the oxidation state of oxygen. So by doing the calculation, we get -half for each oxygen. And therefore, it is superoxide. Okay. Let's do some examples on the next page here. So here you are asked to assign oxidation states for each element in these compounds. First one, again, we go with the element that we know for sure what the oxidation state here. We know we've got 2K plus, right? Therefore, sulfur has to be 2 minus. Okay, so the oxidation state of sulfur is -2. And next one, again, we go with the cation because this is a group 1 element. So we've got 2 sodium plus. This means that we have oxygen in the -1 oxidation state. Okay, in reality, it is O2. It's actually this. I shouldn't write it like that. It is O2 2 minus, but then the oxidation state of 1 oxygen is -1. Okay, I shouldn't write it like this. So therefore, oxidation state of 1 oxygen is -1. So we have again here a peroxide. Next one, we go with the cation. We know this is a group 2. Use your periodic table on the exam if you're not sure. This is a group 2 element. So therefore, it can only have +2 oxidation state. Therefore, again, we have the O2 2 minus ion. Therefore, okay, for oxygen, I'm just not going to write that again, is -1. So we have a peroxide again. Now the last one. Now, a lot of questions come around these. If you see anything like these polyatomic ions with oxygen in them, usually you will see they will contain a high number of oxygen. What you do then, you take the oxidation state for oxygen to be -2. Okay, just the normal general one. It's -2. You see we have chromium here. Chromium is a transition element. It can have different oxidation state. It can be +2, it can be +3, it can be +6. So we have to find out what is the oxidation state of chromium here. So here we'll go with oxygen. So we will say oxygen is -2. Therefore, we've got 2 chromium. We've done this before, I think, times 7 oxygen. The sum must be equal to the overall charge. Therefore, 1 chromium is +6. Okay, so that's how you find the oxidation state. Now let's do some more practice and then we will get to something else, another definition that I want to go over with this reaction. So here, let's say given an equation like this, okay, and we have all molecular compounds here, and you're asked to assign oxidation states to each element and then to tell which one has been oxidized and which one has been reduced. So in terms of the change in their oxidation state. So I'll start with this oxide of iodine. And again, like I said, if you see compounds like that with, 3, 4 more oxygens in it, then yes, you go and you write down the oxidation state for oxygen to be -2, then use that to find the oxidation state of the other element. Okay, so here, if we do that, we will see iodine is in the +5 oxidation state. At the end, if you want to stay back, if you're having trouble finding these numbers, let me know. I will show you stepwise how to do it. Okay. Now we look at carbon monoxide. Again, that's a normal oxide. Oxygen is -2, which means that carbon is in the +2 oxidation state. Here, diatomic homonuclear molecule, oxidation state of each atom is 0. Here, -2 for oxygen, therefore carbon is +4. Okay, now we will look at how the oxidation state of each element has changed in this reaction. Iodine went from being +5 to 0, so that's a decrease in oxidation state, therefore this is reduction. And if we look at the oxygen as well, we can tell, right? It went from the oxide to the element. So decrease in oxidation state, reduction. For carbon, like I said, if there is reduction, there has to be oxidation as well. +2 to +4, that's an increase in oxidation state, therefore we have oxidation. Carbon is the element that has been oxidized in this reaction. Okay, so you can tell why being able to find oxidation state is important. In the next one, I'm going to write all the oxidation state for you. And then, like I said, I will talk about some definitions. So here, you can go with either oxygen or hydrogen. It's easier to do it with hydrogen. We know it is bonded to a non-metal, so therefore each hydrogen is +1. Oxygen is -2. Okay, these two added together gives us the -1 charge on the hydroxide ion. This, we just did that. Oxygen is -2. Each chromium is +6. If you work out the oxidation states here, again, by posing oxygen to be -2, you will see chromium is still in the +6 oxidation state. Here, just water, -2 and +1. Again, when I'm writing these numbers, I repeat myself here. I'm writing the oxidation state for one atom in that molecule. Okay, so that +1 there is for one hydrogen. So what we see here, oxygen went from -2, of course, -2 at the end. And then all the other elements, they didn't change oxidation state. So this type of reaction then is not a redox reaction. There has been a reaction, reorganization of bonds, but we see there has been no change in the oxidation state. Okay, so it's not a redox. What it is, we call it it's a special type of reaction. We call it a disproportionation reaction. And disproportionation reactions, they are of two types. Okay, the first type is this, where we see no changes in oxidation states. Okay, so it is not a redox. The second type of disproportionation reaction is one where we see an element undergoing a change in its oxidation state, but the same element, that one element, it will see an increase in its oxidation state as well as a decrease. So both happen in the same equation. I'm going to give you an example here. First definition. So it is a redox. Okay, so in which one species is simultaneously oxidized and reduced. Okay, so in that same reaction, let me give you the example. So here, we take this mercury chloride. This is a 2 here. Okay, so mercury 2, Hg2, Cl2, forming mercury and okay, so that's mercury 1 chloride giving mercury and mercury 2 chloride. If we look for the oxidation state, this is a halogen, it is -1. So we know mercury here is in the +1 oxidation state. Here, of course, it is the element. It has no charge. And in here, chlorine is -1 still. And this is a +2 oxidation state. So we see it is forming two different compounds. Going from the initial one to one compound, it sees a decrease in its oxidation state, and when it makes the other one, we see an increase in its oxidation state. Okay, so we see, of course, from here to here, that's reduction. Okay, and from here to here, this is oxidation. Okay, I apologize for my handwriting here. I'm just haven't positioned my tablet in properly in front of me. So this is reduction. Okay, so we see both. Another example is when, remember I did this demo where I used hydrogen peroxide. The reaction was catalyzed to form water and oxygen. So in that, if you write the equation for that reaction, so H2O2 giving H2O and O2, so oxygen, you will see that oxygen goes from having a -1 oxidation state in hydrogen peroxide to a 0 oxidation state in oxygen and to a -2 in water. So that is also a disproportionation reaction where we see the same element undergoing oxidation and reduction. Okay, I won't write it down, but it's just another example. If you're curious, you can check the oxidation states. Now, something very important, and I'm hoping I'm able to get through these next 2 slides in the time that we have today. I will be showing you how to balance redox reactions. And you will see these redox reactions, they are complex reactions, and they take place either under acidic conditions or basic conditions. So I will show you the steps. They differ slightly. What to do when you are balancing, and you will be told in the exam. If you're given this on the exam, you'll be told balance this equation or this reaction, which is taking place under basic or under acidic conditions. So you will know exactly what steps you need to follow. You will see there are many steps, but with practice, it will become easy to do. Okay, and there's a whole bunch, a list on eClass for you to practice. You can take a look at it after lecture today. So what we do, normally you'll be given an equation like that and told what are the conditions of the reactions. First, the very first thing you do, whether it is basic condition or acidic condition, is you identify the 2 half reactions. This is called the half reaction or half equation method. Okay, so here I have ClO minus, and this is giving me Cl minus on the product side. So this will be my first half reaction. Just write it down like that. Basically, I'm just looking whatever has chlorine at the beginning, and I'm looking for chlorine in my products. So that will make my first half reaction. The other half reaction is CrO giving me chromate. That's your very first step, okay? No matter what the condition of reaction is. Then the second step is to follow these 6 steps in order to balance each, okay? Each of these 2 half equations that we have written here. We'll do one at a time. So we'll take the first one. And it says here, assign oxidation states to all elements of the equation. I'll take the first one. And I need to assign oxidation state, like I said, for compounds that you cannot tell the oxidation state for the other element for sure. Like, for example, if it is not a group 1 or group 2 element, then you go with the -2 oxidation state for oxygen. So I'll just do that here. And that will help me obtain the oxidation state for chlorine. Okay, remember the halogens, they are not always in a -1 oxidation state. Okay, so here, as we see, if I do that and I use the overall charge on this molecule, I will obtain a +1 oxidation state for chlorine. And here I just have Cl minus. It already has the charge indicated here, so I don't need to do anything. So when this is done, I move to the next step. Now, next step tells me balance the elements that have had a change in their oxidation state. So in my equation, I only have 2 elements, chlorine and oxygen. I have oxygen on only one side. I don't have oxygen on the other side of my equation because it's not balanced yet. So I look at chlorine, And I see that I have one chlorine on each side of my equation. So I'm good. Okay. So here in this case, it is already balanced. If it's not, you balance it. Okay. So tick, I move on. If something is already done, then you don't need to do anything. Move to the next step. Now, next step is to add electrons in order to balance the change in oxidation state. Okay. So what we see, I'm going to write this again, ClO minus giving me Cl minus. Now, I need to balance the change in oxidation state. As I said, we do not need to worry about oxygen here, okay, because it is only on one side of the equation. Chlorine is changing from oxidation state of +1 to an oxidation state of -1. I need to balance that change, okay, from +1 to -1 by adding the right number of electrons to the right side of my equation, okay, to the correct side of my equation. So where do you think I will need electrons? On the reactant side or product, and how many?
You'd need 2 on the reactant side, right?
Okay, perfect. Okay, thank you. So we will need 2 electrons on the reactant side in order to balance. Okay. All right, someone has, that was cute, but at first I thought somebody fell or something. I hope everything is okay. Please turn off your mic. Thank you. Okay. Yes, so we need 2 electrons to balance this charge, okay, this change in oxidation state. As you can see, +1, 1 positive charge plus 2 negative charges gives 1 negative charge, right? And we have 1 negative charge on the product side. So this is good. Then we move on to the next step. Okay, as you can see, at first it looks like a lot, but when you practice, you will know what to do. Because this reaction is taking place under basic condition, so we need to now add OH minus, and we will do that in order to balance the charges. Okay, so now I'll write it again. So this is what I have so far. I want to add OH minus to balance charges. Right now, I have 3 negative charges on my reactant side, but only 1 negative charge on my product side. So therefore, I will have to add 2 OH minus in order to balance the charges. Now I've got 3 negative charges on both sides. Because I have introduced hydrogen now through hydroxide, I will have to add water molecules in order to balance the hydrogen. Okay. So I have introduced 2 hydrogen in my equation. I will need 1 water molecule in order to balance this hydrogen. Okay. Then in the end, you just need to check if all the oxygens are balanced. Let's count. We've got 1, 2 on the reactant side. We've got 2 on the product side. So we have a balanced half equation. What type of half reaction is this? Is this our reduction or oxidation half reaction?
Reduction, half reaction.
Yes, perfect. Thank you. Because there's gain of electrons here, this is our reduction half reaction. Yes, Nikala?
So just for the last step there, what would we do if the oxygens were not balanced?
Good question. If your oxygens are not balanced, it means that you have left a mistake in the previous steps. So that's an indication to go back and check. Because if everything is done correctly, it will balance in the end. Okay. It's actually, that's how you check if you've done everything well. Okay.
Thank you.
All right. So now we'll balance the second half equation. We'll go through the same set of steps to balance it. So again, first step is to assign oxidation states. So here -2. So therefore this is +2. And in here, again, -2 for oxygen. Chromium is in the +6 oxidation state. Okay, next step is to balance the atom or the element that has had a change in its oxidation state. So we can forget about oxygen here. It goes from -2 to -2. We do not have to worry about it. Chromium has changed oxidation state. We need to balance it. We've got 1 chromium on each side. We're good. Then we will add electrons to balance this change in oxidation state. Okay, so oxidation state, we're going from +2 to +6. How many electrons do we need and on which side? Anyone?
Is it 4 on the product side?
Very good, thank you. So we need 4 electrons on the product side, okay? So which also makes sense. We just obtain our reduction half reaction, okay? So it will make sense that electrons in our second half reaction will be on the product side, then it will be the oxidation reaction. So we are good. Then next, we need to add OH minus to balance the charges. Okay, so now I can get rid of these. I've got the right number of electrons on the right side, on the correct side of my equation. Now I will add OH minus to balance charges. I've got 2 negative charges and 4 negative charges, so 6 total on the product side. No charges at all on my reactant side, so I need to add 6 OH minus. This balances the charges. Now I need to balance the hydrogen. I have introduced 6 of them. Therefore, I will need 3 water molecules to balance them. Now let's check if oxygen is balanced. We've got 1 here and 6 here. So that's a total of 7. We've got 4 and 3. That is 7. So it is balanced. So the goal is to balance all the atoms, all the elements in your equation, and also all the charges. Okay. So now that we have this is our oxidation. Half reaction. Now we need to put them together. Okay, we can't leave them like that because our goal is to build the balanced chemical equation for this redox reaction. Now, always remember your final equation, your balanced redox equation can never contain oxygen in them. Can never contain electrons in them. Okay, so we will add these 2 half reactions in order to cancel out electrons. Okay, so what we see, I'm just going to rewrite my reduction half equation here. Okay, first is oxidation, second one is reduction. I want to add them so I can cancel the electrons and build my overall balanced equation. But my problem here is that I've got 4 electrons in the oxidation reaction, but only 2 in my reduction reaction. So what I will do is I have to multiply my reduction equation by 2 in order to obtain 4 electrons. Okay, so this needs to be multiplied by 2. Yes, Matthew?
Can you hear me all right?
Yeah.
Okay. I'm sure I might have just misheard, but for a balanced, or sorry, not a balanced one, but just for those half reactions, are we supposed to list the electrons in that statement, or is it just the atoms?
Oh, the electrons need to be included because we are
Okay.
writing half reactions.
Okay, perfect. That's what I
Okay,
thought.
electrons are always involved in half reactions, and but not in the overall.
Right. Oh, no. Gotcha. Okay.
Right. So then what I did here, again, I multiplied by 2 so I could make the number of electrons in the second equation the same as in the first one. But when I do that, do not multiply just the number of electrons. You have to multiply everything in that half reaction by 2. Then we add them.
Right, of course, because we want the
We want only
charge.
yes. We want only electrons to cancel out, right? So when we do that, we will see we've got 4 electrons on product side here, 4 on reactant side. They cancel out. And then we start writing our overall equation. So let's do that. And students ask this question, in which order should we write them? It doesn't matter which one you write first, second, as long as everything is there and it is balanced, you're good. So I'll choose to put CrO, so chromium oxide, and then I'll put the other one. Okay, now I've got 6 OH minus on the reactant side here, and I've got 4 OH minus on the product side. Okay, so this leaves me with 2 OH minus on my reactant side in my main equation. Then I look at water. I've got 3 water molecules on product side, 2 on the reactant side. This will leave me with 1 molecule of water on the product side. So I continue writing the products plus 2 Cl minus plus 1 water molecule. So this now is my balance redox equation. Check it one last time once you get to this point. What we are checking for is if all the atoms are balanced and also if the charges are balanced. This is very important, okay? So 1 chromium, we are good. 2 Cl, 2 Cl, good. Oxygen, the balance, we've got 2 and 2, 4, 5. We've got 4 and 1, 5. Check. Hydrogens are balanced as well. Check the charges. We've got 2 negative and 2 negative, 4 negative charges on the reactant side. We've got 2 negative and 2 negative charges here, 4 on the product side. So you see it is balanced. So as you see, if each step has been done correctly, you will end up with a balanced equation, everything. Okay. Any questions or comments?
Yeah, Professor, I have a question.
Mhm.
If this reaction were under acidic conditions, I don't know if that's where you're going next, but
Yeah.
what would we add instead of OH negative?
Okay, so then these are the steps. Okay, maybe now that we have gone over the balancing of the reaction in basic conditions, follow the same steps here, these steps, and try to balance this redox reaction. Now this one is taking place under acidic conditions. The first few steps, they are identical to when we are balancing in basic conditions. That is, we write down the 2 half equations to identify them, write them down. Then use this set of rules now to balance each one. The first 3, as you can see, assign oxidation state, balance the element that changes oxidation state, add electrons to balance the change in oxidation state. These 3, they are the same as before. Okay, same as in basic conditions. Where you will see the change now is the 4th step. Now, instead of adding OH minus to balance charges, we're going to add water to balance the oxygens first. Okay. Now, when we introduce water molecules, we have introduced hydrogen. So then we add H plus because it is acidic condition. We add H plus to balance the hydrogen. And in the end, we check if all charges are balanced, and they will be if everything has been done correctly. Okay. So here I will write these 2, Cr2, O7, 2 minus. That's my first half equation. And I minus giving iodate is my second reaction. I see there are questions. Matthew, is that from earlier?
Yes, it is. Sorry.
That's okay. Olivia?
Hi, so in high school, I remember doing this, but the steps were in a different order. So we were balancing the O and the H and then adding electrons after. Does that work, or is it supposed to be like this way?
Okay, yes, I forgot to mention that. I know you may have learned different methods, and that's okay. But the thing with okay, so when we were in person, I used to tell students, use the method that you are more comfortable with. But the thing is, and this is from experience from testing online last year, is I will be asking you questions based on this method. Okay, so either I can put that as a question that you will have to write down and upload, Maybe that is the option. Or I can ask, for example, how many electrons are required to balance this this half equation or the oxidation half equation of the reaction. So then you will have to follow this method. So yeah, but I think, you know, I can always have you upload your answer for these types of questions. So if you're comfortable, or if you've learned a different method, go ahead and use it, but please show your steps.
Okay, thank you.
Okay. All right, it is time. I will stop here, but I will say this before you go. Please